So we've learned about atomic radius already, but what about when we start to get ions, like magnesium losing electrons to become a +2 ion? This is its common ionic state. Well, from magnesium to magnesium 2 plus, that's pretty easy. We're clearly going to get smaller because if we lose two electrons, those two electrons, well, then we're going to lose a whole layer. If we lose a whole layer, just like peeling an onion, we're definitely going to get smaller. But what if we just lose this electron? And now we're just left with that single electron in our outer shell. Do you think we'd get smaller, stay the same size, get bigger? Well, we haven't really factored this in yet, but there is some repulsion from these inner electrons. These electrons are going to be pushing away. This electron is going to be pushing back at them. And so that mutual repulsion is going to cause this whole layer to get pushed out a little bit, because this electron is also going to be having those forces, right? Well, if I remove one of those electrons, then there's just one electron here to be pushing back at these. And so when I remove one electron, my radius goes down. And so as my charge increases, my radius decreases. So that's a rule of thumb that we can follow, is that my charge is going to be inversely proportional. So inversely proportional, this is how we write this, to my radius. So when I've got a charge, this symbol means proportional, and 1 over my radius means that as my charge goes up, my radius goes down, and vice versa. So if my charge were to go down, like let's say fluorine going to F minus, what would happen to the radius? Well, the charge went down, so the radius would go up. So here I've got a radius, and here I've got a bigger radius. It's going to increase in size when it ionizes. Okay, so that should be pretty intuitive just because we're thinking of these forces according to Coulomb's law here, but how could I compare the sizes of these atoms? Because once we start getting into ions, if magnesium goes to magnesium 2 plus, is that going to be bigger? Is it going to be smaller than neon or sodium? I think those are right next to each other on the periodic table. That kind of breaks that periodic trend that we have. So we can't just look at the table anymore. And so what we do instead is we use this thing called the effective nuclear charge. And that's what this equation right here is. ZF is the effective nuclear charge. F stands for effective, Z stands for nuclear charge. And nuclear charge is really going to be my number of protons. So we're going to start with Z, which is going to be my number of protons. And then my S right here, we're going to subtract S. This is going to be my inner shell, so inner shell electrons. So if I go back to my magnesium example over here, my inner shell electrons are all of them that are on the inside, anything that's not on the outermost shell. So for magnesium, I would have these 8 plus these 2, I would have 10. For this one, I would have 10 for magnesium 2 plus. Well, I lost that outer layer, so now this is my outermost layer. And so suddenly I only have 2. So for this, my S would be 10. For this one, my S would be 10. And for this one, my S would only be 2. And so a quick way we can look at this, since we are using a simplified version of the effective nuclear charge equation, a quick way we can look at this is, what's the previous noble gas? We can subtract that number. So for magnesium and magnesium plus 1, the nearest noble gas, the most previous noble gas would be neon. And neon has an atomic number of 10, so we can just subtract that as being the number of electrons on the inside here. That's a little shortcut that we could use. But let's go ahead and calculate this. So when I say effective nuclear charge for this magnesium, what I'm really saying is, what would be the numbers that I would put in this Q1 and Q2? In order to account for the fact that I've got protons here pulling this electron in, and electrons out here that are pushing this back out. Well, that Z effective nuclear charge would then be my Q1. And then my electron here, that would still be its normal charge of -1. So let's go ahead and calculate this for, let's just say, regular magnesium, and then we'll do magnesium 2 plus. So my effective nuclear charge for magnesium, this is going to be my number of protons, which for magnesium, Z is 12, minus my inner shell electrons, which, once again, this would be 10. So for regular magnesium, my effective nuclear charge is 2. When I lose these 2 electrons and go to magnesium 2 plus, what does my effective nuclear charge become? Well, I still have 12 protons, but now I only have 2 inner shell electrons. And so I'm going to have an effective nuclear charge of 10. So we could say there's a lot more of a force pulling these electrons in. Now, Doing this method isn't going to work super well when we're going just from magnesium to magnesium plus, because we are going to use a simplified version of this equation. There is a more complex version that we can do where we account for electrons in the same orbital, but that's a little outside of our scope. So when we're just looking at one charge difference here, we are going to need to rely on this trend, that our radius is going to go down as our charge goes up. So you'll need to just remember this or write this down. But when we are comparing different atoms, the effective nuclear charge will be very handy. So let's look at aluminum 3+ versus neon versus O-. And let's compare what our radiuses would look like here. So for aluminum 3+, what is my number of protons? Well, that's going to be 13. What's going to be my number of electrons? Well, 13 is my normal state. So plus 3, I lost 3 electrons, so I'd have 10 electrons. So what's going to be my inner shell? Well, if I look at 10 on the periodic table, that's neon. So that's going to be just like that magnesium I had over there. And so this S would have to be 2. So 13 minus 2 gives me 11. Now let's look at neon. Neon has 10 protons, and it's got no charge, so it's going to have 10 electrons. And so 2 of those electrons are going to be inner shell electrons. 10 minus 2 is 8. And then when I look at O-, O, oxygen, is 8 electrons. O- is going to have 9 electrons, or I'm sorry, I should have said 8 protons here. Those will be 9 electrons. And then my S, well, my next lowest noble gas is helium with 2. 8 minus 2 gives me 6. And so the way I use this effective nuclear charge is I consider that to be my Q1 in Coulomb's law. And so the higher this number, the higher the force, which means the lower the radius. And so aluminum here is going to have the lowest atomic radius, followed by neon, followed by oxygen. So how about this one? How about copper 2+, gallium, and selenium minus? Copper 2+, copper is going to have 29 protons. At 2+, it's going to have 27 electrons. And so where S, if I look at the previous noble gas, it's going to be argon at 18. So 29 minus 18, it's going to be 11. Now when I look at gallium, gallium has a effective, or 31 protons. It's going to have 31 electrons. And its previous noble gas, once again, is going to be argon at 18. So 31 minus 18, 1 minus 18, that's going to be 13. Okay. And selenium, selenium's number of protons is going to be 34. And my number of electrons here, well, that's going to be 35. So it's got a charge of -1. So S, once again, they're all in the same row. So once again, it's going to have 18. 34 minus 18, it's going to be 16. And so here I have the opposite effect. So my Zeph being 16 means selenium is going to have the lowest radius. Then gallium is going to beat out copper 2+ with a Zeph of 13. And so copper 2+ is still going to be larger than gallium, which is still going to be larger than selenium. Fantastic.